In this video, we would introduce our work, LightGaussian, a framework designed for representing 3D Gaussians into a more efficient and compact format. Novel View Synthesis, or NVS, aims to generate photorealistic images of a 3D scene from unobserved viewpoints, given a set of calibrated multi-view images. NVS holds importance as it can be used for a wide range of real-world applications, including virtual reality, augmented reality, digital twin, and autonomous driving. Neural radiance fields, or NeRF, have demonstrated promising ability for photorealistic 3D modeling and synthesis from multi-view images. However, MLP-based NeRF has struggled with rendering speeds for practical deployment in real-world scenarios. For example, MIP NeRF 360 runs at only 0.06 FPS on the unbounded scenes. Voxel-based NeRF, for example, Instant NGP, improve the rendering speed to 10 FPS, but the performance still lag behind the MLP-based representations. Therefore, NeRF-based methods hardly balance between the rendering speed and quality. Recent progress in point-based 3D Gaussian Splatting, or 3D GS, has brought photorealistic rendering quality to the real-time level, even for complex scenes. The authors propose representing the scene as explicit 3D Gaussians with specific properties to model the scene. The 2D images are efficiently rendered using a technique named splatting. The optimal balance between speed and quality indicates a potential trend to use 3D GS as a new representation for generating numerous large-scale scenes. However, using point-based representations inevitably introduces significant storage costs, as each point and its attributes are stored independently. For instance, 3D GS on a typical unbounded 360 scene requires more than 1 GB, which inhibits the scalability of 3D GS. In this paper, we counteract the heavy storage issue and deliver a compact representation while preserving the rendering quality. By examining the well-trained point-based representation, each scene is composed of millions of Gaussians, grown from sparse structure from motion point cloud. Attributes are attached to Gaussians to model the scene's geometry and appearance. However, the significant number of Gaussians inevitably contribute to a heavy storage size. The second challenge is the high-degree spherical harmonics, SH, coefficients used for modeling scene specular effect, contribute to an overparametrized representation when fitting to the scenes. Lastly, similar attribute across Gaussians can be quantized or compressed into lower bitwidth representation, to reduce the saved model size. Simply utilizing Gaussian opacity as an indicator for pruning the least important Gaussians results in the rendered image losing intricate details, with the PSNR dropping from 27.2 to 25.3. This has inspired us to find better criteria to measure global significance in terms of rendering quality. In the first challenge, we propose proper criteria to measure the global significance of each 3D Gaussian, in the context of its contribution for view synthesis. Gaussians with low impact on visual quality will be identified and pruned, followed by short recovery steps to be applied. This can minimize the required Gaussian number for modeling a 3D scene. Inspired by rendering equation, these 3D Gaussians can be rasterized by projecting them onto a specific camera viewpoint for image rendering. The significance of each Gaussian can then be quantified based on its contribution to each pixel across all training views, with similar principle in magnitude network pruning. Consequently, we iterate over all training pixels to calculate the hit count of each Gaussian, factoring in both Gaussian opacity and volume. In the second challenge, the high-degree spherical harmonics, SH, coefficients used for modeling scene reflection, contribute to an overparametrized representation when fitting to the scenes. However, compressing it directly by shrinking the higher degree harms the reflectance effect, and we propose a general distillation step enhanced by pseudo-view augmentation to harmlessly transfer the knowledge into a compact level. In the last challenge, the vanilla vector quantization can further reduce model size. Unfortunately, such lossy quantization significantly drop the modeled accuracy when applied to all attribute. We empirically found that the Gaussian location and its shape attributes are sensitive to vector quantization, and therefore we propose a hybrid compression for further compressing Gaussian attributes. The proposed VecTree Quantization, which contains the lossy vector quantization on the redundant spherical harmonics, as well as the lossless octree compression on the Gaussian location. The hybrid quantization further reduces the required bit width of the original format. LightGaussian first calculates the global significance for each Gaussian based on training observations. Gaussians with the least significance are pruned. A subsequent distillation with synthesized pseudo-views is introduced to transfer the SH into a compact format. VecTree Quantization, consisting of lossy codebook quantization and lossless octree quantization, is further introduced for compressing the representation. LightGaussian effectively prunes redundant Gaussians while preserving visual fidelity. Consequently, it reduces the average storage from 727 megabytes to 44 megabytes and improves the FPS from 139 to 215. We compare LightGaussian with the original 3D, GS, efficient voxel-based NeRFs, voxel NeRF with vector quantization, and compact MLP-based NeRF. Voxel-based methods all exhibit a lack of sufficient capacity for representing large-scale scenes and are not able to run at real-time speed. MIPNA-RF 360 produces the best visual quality, but it requires more than 16 seconds to render a single image. Our method achieves a good balance among FPS, model size, and rendering quality. The ablation study validate that zero-shot Gaussian pruning leads to a degradation in rendering quality, number 2, but co-adaptation can recover most of the scene details, number 3. Directly eliminating high-order SH negatively affects the quality, number 4, while distillation with pseudo-view helps to mitigate the gap, number 5, number 6. Codebook quantization significantly reduces the required model size, number 7, while lossless octree compression helps to preserve the overall quality. We compare LightGaussian with the vanilla 3D, GS, presenting a residual map between prediction and ground truth to highlight the differences. We observe that LightGaussian preserves the specular reflections after converting to a compact format. Additionally, a slight lightness change is noted after the conversion, as shown in the bottom white box. Here are the visualized results of LightGaussian compare with 3D Gaussians. Experiment is on Scene Garden. More visualizations on Scene Stump are shown here. Thanks for watching the video. Please refer to the main draft for more technique details.